Hello everyone and welcome back to your YouTube channel and welcome to this very exciting video of today. As you must be aware, I am recording this series of videos that I call Fundamental of Power Engineering. And the series of videos is dedicated for some of the general public without any background on electrical power systems, but they are interested to go into this amazing and lovely world of power engineering. So for that reason, I am recording these very simple, straightforward videos dedicated to solving numerical examples and problems related to basic fundamentals of electrical power system. So without further delay, let's go and let's start the solution for the video today. So here we are here inside MATLAB live script. As you must be aware, I am using this amazing tool for my numerical examples because I want to focus on the explanation, the solution methods, and also the understanding of the solution instead of focusing on the numerical part. So I am using this MATLAB live script because they allow me to write this iterative document that you can read my tips, my explanation. At the same time, you can see and you can watch some figures and also some equations. So without further delay, let's start with this description over here. And let's start with this example that is related to steady-state power in single-phase system. So let's read over here. Consider a 230 50 Hertz power supply, which is connected to a static load represented by RLC. Remember, RLC series is indicative of resistance, inductance, and capacitance, all of them connected together in a series connection, where the resistance is 3 ohms, the inductive reactance is 6 ohms, and the capacitive reactance is slightly smaller, is only 2 ohms. There are a few questions over here. Calculate the total series impedance in ohms. Remember that the impedance is a complex number, so we want the polar and the rectangular representation of that complex number. Question B, calculate the current in the circuit. In this case is the current I in amps. Again, this is a phasor, so we need the polar and rectangular representation. Then question C is calculate the magnitude of the complex or apparent power. And again, remember that this complex power S in volt amps is another phasor. This is another complex number. So we want the polar and rectangular representation. Then question D is calculate the active power P in watts. Then question E is the reactive power Q in volt amps reactive. F is calculate the power factor, in this case at the power supply point. And G is to draw the power triangle. So without further delay, let's start the solution of this problem. As you can see, I create here the circuit representation for you. Remember, we are using AC quantities, steady-state AC quantities, so the voltage, the currents, they are complex numbers. So that is the reason that we are using these capital letters to represent in italic that they are phasors. So here we know that the magnitude of this voltage is 230. We know that the frequency is 50 hertz. We know that the resistance here for this resistor R is 3 ohms. We know that the inductive reactance is given is 6 ohms, and the capacitive reactance is slightly smaller, but remember this is minus J, and that is 2 ohms, okay? So the first step is extremely simple, because what you need to do is to calculate the total series impedance set, and in this case set is basically using a complex number representation. The real part is the resistance. In this case, we know that the resistance is 3 ohms, and the imaginary part is connected with JXL, and XL is 6 ohm, representing the series inductive reactance. And then we have the negative for the capacitive reactance. In this case, is 2 ohms. So we use our amazing calculator here, and we obtain the rectangular representation is 3 plus 4 ohms, J 4 ohms. And the polar representation is 5 with a phase angle of 53.1. So when we know the impedance, now it's time to calculate the current. And the current in AC system is very simple to calculate, because we can use the amazing Ohm's law. So taking the current from the Ohm's law, we can easily say that the current is the voltage divided by the impedance. So assuming that the voltage source is the reference, so it's 230 volts, 0 degree. And the impedance, we already know, 3 plus 4J. So when we put that in the calculator, we obtain the amazing current that, if you are using the rectangular representation, will be 27.6 minus 36.8 J's amps. If you prefer the polar representation, is 46 amps with a phase angle of minus 53.1. Next step, well, we need to calculate the apparent power. And every single one of my students, they must remember the beautiful equation for the apparent power. And the apparent power is the product between the phasor V, representing the voltage, and multiplied by the conjugate of the phasor current. So that is the reason for this amazing and beautiful symbol over here, this asterisk, that is representing a mathematical function that is called the complex conjugate. The good news is that inside MATLAB there is a function that is called conjugate. So I put here the voltage, 200 volts, 0 degree. We know the current, that is 45 at minus 53 degree. But when we apply the conjugate, we obtain here the power, the apparent power. You can see that if you prefer the rectangular form, is 6,348 plus 8,464 J volt amps, or using polar representation 10,580 with a degree phase angle in degrees of 53.3. There is no surprise. The angle of the apparent power is the positive of the angle coming from the current. In this case, the voltage is a reference, so when we apply the conjugate, this negative is becoming positive. So there is no surprise over there. So then we extract the active power, and the active power is the real part of the apparent power. In other words, 6,348. That is the answer for question D. And also, similarly, we can apply reactive power is the imaginary part of the complex power. In this case, 8,464 volt amps, okay? Now, question number F, or letter F, we need to calculate, we need to know the value of the power factor. And the power factor is the cosine of the power angle. So we can use this power angle here, 53.13, that we already calculated, and we calculate the cosine of that. Or if you prefer, you can divide the active power, 6,348, by the total apparent power, that is the magnitude, 10,580. In any case, we obtain a very poor, very low power factor. You can see over here, 0.6 or 60%. That is a very ugly low power factor. So finally, we have been asked to plot the power triangle, and I am using here MATLAB. So you can see the horizontal axis is the active power, in this case, 6,348 watts. Here in the vertical axis, you can see that this is the reactive power, Q, and that is 8,664. And here in this side, you can see the magnitude of the apparent power, and in this beautiful case today is 10,580 volt amps. So this has been an amazing example about AC steady-state power in a single-phase circuit. And we are reaching almost the end of this video. I would like to invite you, all of you, to subscribe and be part of the community, be part of LinkedIn, YouTube, and Twitter, and Instagram. But sadly, we are reaching the end of this video, and today you learn about calculating power in AC systems, and that's all for today. And the only thing remaining is the classical bye now.